I'm audible. Scribes for today, ID number 162. Are you there? 163?
Yes, sir.
164? 165?
Yes, sir.
166? 167? 168? 169?
Yes, sir.
Okay. And 170. To the best of my knowledge, this is the last ID number in our section. In case I missed anyone, please let me know. Remember, if you are not assigned to a particular group on Moodle, that means your scribe, you're not considered as a scribe, and if that is the case, you will not receive any marks for your scribe notes. Okay. Right. Okay, so let's get started, I think. 3 now. Okay, so just to recap what we did in the previous class, we introduced two new tools that a vector space can be equipped with. Again, the condition is that the vector space should be defined over either a set of real numbers or the set of complex numbers as fields. Okay, once we have an inner product, then we get a norm definition for free. Okay, that norm is what is called the induced norm. Once we have an inner product defined on a vector space, we can define what is known as orthogonal and what we have been calling till now as perpendicular vectors. Okay, but the crucial difference is the definition of perpendicularity is sort of hardwired with us. Okay, whereas in more abstract sense, orthogonality depends on what is the inner product that your vector space is equipped with. Okay, so you have two vectors being orthogonal if the inner product is 0, and these orthogonal vectors are also orthonormal if they are unit vectors, where the unit comes from the norm, specifically the induced norm only. Okay, given set of n vectors is said to be orthogonal if the inner product of any two distinct vectors is 0, and this set is said to be orthonormal if, apart from being orthogonal, they are all unit norm vectors. If set of orthonormal vectors also forms a basis, then we get what is called an orthonormal basis. Okay, by the way, a quick question here. If I have, let's say, n vectors which are orthogonal, are they necessarily linearly independent? Could anybody answer that question? Does orthogonality imply linear independence? Anyone? You care
Not
to answer
always.
this? Not always. Okay, can you give me an example where this is not true?
When two vectors are perpendicular.
Okay, so they are okay. Let's talk about this case.
Yes.
So aren't they linearly independent?
No, the inner product not necessarily linearly independent. Inner product will be
These-
0, but
But aren't these two vectors linearly independent?
Sir, I think it depends on the definition of inner product.
Acha. Okay. Anybody else? This is linearly independent, right? I mean, that I hope all of you agree with. Okay, maybe let's quickly try to see if this is possible. So let V1 to be N be an orthogonal set of vectors with one assumption extra. None of them is the zero vector. Okay, and let's assume that the set is linearly dependent. So by definition of linear dependence, what does that mean?
A1, V1, A2, A2 is equal to 0.
Scalars such that A1, E1, so on and so forth, AN, VN is equal to 0, and
A is not the zero vector.
not all AIs are 0. And AIs are not the vectors, remember, scalars.
Sir, I meant the vector formed by AIs.
Oh, okay, okay. Fine, so this is 0. Then, so what happens if I take inner product with V1 on both sides? What happens to the left hand side?
So it will be 0.
How would the left hand side be 0?
No, sorry. A1 times V1 inner product of V1 with V1.
So that is norm
Norm of V1
V1
square.
squared. Then what else?
All others are 0.
Yes.
All others are 0 from orthogonality. So this is equal to, what would be the right hand side? V1 inner product theta is of course 0.
0.
So what does this imply?
A1 is 0.
A1 is 0. Similarly, so if I make this into a general thing, take inner product with Vi on both sides, what happens? Basically, AI Vi naught squared equal to 0, and once again we can see crucially this plays a role. If Vi, any one of Vi is 0, right, the set of vectors can still turn out to be orthogonal, but surely it will not turn out to be linearly independent. Okay, but now I hope you can see that as far as I have a set of orthogonal vectors where none of the vectors is the theta vector, then they have to be linearly independent. Okay. Please see that I did not make any assumption on what the vector space is. Okay, in any inner product space, this has to be true. So the inner product could itself be arbitrary, the vector space could itself be arbitrary. This has to be true. Okay. Is that convincing?
Yes, sir.
Yes, sir.
Right, then let's quickly go ahead and try to derive some properties. Name of this proposition could be a little surprising for you. This is something you've studied in your school, Pythagoras theorem. But in your school days, you would have studied Pythagoras theorem only in R2. Okay, we are studying the more general version of the Pythagoras theorem, okay, which states that in an inner product space, if two vectors are orthogonal, then the norm squared of the sum of these two vectors is equal to sum of the norm squared of the two vectors. Okay, so this is my vector x, this is my vector y, and both of them are orthogonal. X plus y would be this vector, right? Okay, so I think from the drawing you recognize this is a usual Pythagoras theorem. How do we prove this? What is the definition of this?
The inner product of x comma y with itself.
X plus y with itself. Okay, then what do we know about the inner product with respect to its first argument?
It is linear.
Linear. Then about second argument, is conjugate linear, right? So this is equal to x plus y with y, complex conjugate. Similarly, sorry, with x plus complex conjugate of x plus y with y. Now I can use linearity, right, in the first argument. And of course, complex conjugate. So a plus b complex conjugate is equal to a complex conjugate plus b complex conjugate. And then here, what is x inner product x complex conjugate?
The norm of x whole square.
Right, because that is norm, so it is a real number. Real number is equal to its own complex conjugate. What do we know about y inner product x and x inner product y? Because of orthogonality, these are 0. So that is how we prove Pythagoras theorem in a general inner product space. Once again, I hope you appreciate the beauty here in the sense that I did not assume what the vector space is, what the particular inner product is. No matter what your inner product is, this always has to be true. Okay, also, I did not assume any particular vector space. The vector space of functions, Rn, Cn, whatever. Okay. Oh, so I already proved this. Then we are going to talk of something which is going to be very crucial as far as applications are concerned. Theoretically, as such, also, it's a nice concept. So what we are doing over here is, if I give you this vector x, okay, and if I give you another vector a w, okay, can I decompose x into a vector which is along w and a vector which is orthogonal to w? Is that always possible? And if yes, how do I find the two vectors? As far as the drawing is concerned, I'm basically interested in finding out this vector. What my drawing makes. Hence, and this vector. So what would this vector be in blue?
X cos theta, angle between.
Now remember, we cannot talk of cos theta here because x and w could be complex vectors. Okay, so we are again, that is what is the difference between the geometry that you have learned till now, whether in school or in your, in school, sorry. Right there, you always assume you are working in R2 or R3. Right now, we shouldn't make that assumption.
Inner product divided by norms of both.
Right, but I mean, to derive that, all we know is this blue vector is just a scalar multiple of W, right? So
We
let's
can
call it. Yes, go ahead.
we can find the linear combination required for both of these.
Exactly. So, but what is given in the statement is that one vector has to be linearly dependent on W, or in other words, a scalar multiple of W, right? So let's call that vector as some scalar A times the vector W. The other vector, let's call it, oh, I think I've interchanged the notation. So let me be consistent with what I've written in the slide. So let's call this vector in white as Y. So the vector in blue will be A times Y. And the vector that is orthogonal to this blue vector is shown in red. Let's call that vector W. So we need to find basically A and W such that X is equal to A times Y plus W, with W being orthogonal to the vector Y. And all of this rests on the assumption that both X and Y are not zero. Is that okay? So how do we find A and W? These are your two unknowns. Okay. So we know that W inner product Y is 0, right? From this equation, I can just substitute instead of W, X minus A times Y, right? And then using linearity in the first argument of the inner product, I get this expression X inner product Y minus A times Y inner product Y must be 0. So that directly gives me the solution to A. Okay, X inner product Y divided by norm Y squared. Once we have A, we can find W by just substituting A in this equation here. That gives me W equal to X minus A, which is X inner product Y divided by norm Y squared into 1. Right? Any doubts here? Okay, then let's try to prove something, another property or another inequality in this case. Once again, you may have come across this in your signals and systems course. I'm not very sure. Right? This is the so-called Cauchy-Schwarz inequality. What it says is the absolute value of the inner product of two vectors X and Y must be strictly less than equal to the product of the norms of the two vectors. In principle, you have seen this in your school days, right? You usually know this relation. Cos theta between two vectors X and Y in R2 or in R3 or in any Rn is this, right? Now what can cos theta be? What is the range of cos?
-1 to 1.
Minus.
Right. So if I take absolute values on both sides, what can the absolute value of the left hand side be?
0 to 1.
0 to 1. So therefore, is strictly less than 1, and that implies x dot product y absolute value is less than equal to norm of x into norm of y. Okay, now this is, this is the proof if you are working in Rn. But remember, that is not the case with us. We are working in an arbitrary product space. So let's try to show this inequality for any arbitrary inner product space. Now, if one of the two vectors is just your theta vector, then right, you can see both sides will be 0. Okay, so there is nothing to prove there, is trivial. So let us assume both x and y are not 0. Okay, then what have we shown in the previous slide? If x and y are both not 0, we can write the orthogonal decomposition of x in terms of y and a vector which is orthogonal to y. So this is a times y. This is your vector w which is orthogonal to y. Okay, from the previous slide. Okay, so if I denote this by w, I get this as a times y plus w from your previous slide. That okay? Then, so if x can be written as a sum of two orthogonal vectors, right? A times y and w, these two are orthogonal. So I can directly use the Pythagoras theorem. Okay, so the norm of x squared is equal to norm of ay squared plus norm of w squared. What is norm of ay squared? Right, we can use the absolute homogeneity of the norm to get norm a squared, sorry, absolute value of a squared. What is the absolute value of a squared? By norm of y squared, right? So this is xy absolute squared divided by norm y to the power 4 into norm y squared. So that is why in the denominator you will have a square. Okay, so norm of x squared is norm of this plus norm of w squared. What can we say about norm w squared? Can it be negative?
No.
No. So if I leave this term out, I get a greater than equal to relation. Yes, a norm of x squared is greater than equal to absolute value squared of the inner product between x and y divided by norm y squared. Then taking this on the left hand side, I get my Cauchy-Schwarz inequality. Okay. Then let's talk about another tool. Right. So as of now, we have distinguished between linearly independent vectors and orthogonal or orthonormal vectors. So this Gram-Schmidt procedure, right, is a way in which we can convert linearly independent vectors into orthonormal vectors. Moreover, it doesn't just randomly do this. Okay. A specific way in which it does, it ensures that let's pick any, so V1 to Vm is an indexed or an ordered set, right? Assume that. So this index is important. I'm going to convert this m linearly independent vectors into this m orthonormal vectors such that if I pick the first j vectors from the set of linearly independent vectors, then the span of this is going to be a j-dimensional subspace. Similarly, right, if I pick the first j corresponding vectors from my set of orthonormal vectors that this process gives me, right, this will also span a j-dimensional subspace. Not only that, this Gram-Schmidt procedure ensures that both these subspaces are exactly the same. Okay, for not only a specific j, but for all j's going from 1 to n. Okay, that is what is important about this process. Now, before we look at how this process does what it claims to, maybe it's worthwhile considering this question. Why do we need orthogonal or orthonormal vectors? Right? If we don't need them, if we just, so linearly independent vectors are important because it sort of leads to the concept of basis, and any vector represented in terms of linearly independent vectors, we know that the coefficients are unique. Orthonormal vectors also are linearly independent, as we saw. Okay, but why should we sort of stick to orthogonal vectors at all? Is it important? How does it help? One way to translate this question is right from your school days. Why have you been using the x unit vector along the x-axis and unit vector along the y-axis? Is there any reason for that? Anyone?
Sir, so that we can use the magnitude in the individual linearly independent vectors direction.
No, but that is true for any.
No, sir. I mean, so as to separate the magnitude and direction in separately show them both. As in, when we show some vector as in R3 like I cap, J cap, K cap, we can show direction and as well as with the number with that. Suppose I say 3 I cap, 4 J cap, 5 K cap, then I have magnitude of 3 in x-axis, 4 in y-axis, and 5 in z-axis. So I can show magnitude also, and at the same time I'm also showing direction.
But that is also true for linearly independent vectors. So if I write x equal to some a1 v1 plus a2 v2 plus a3 v3, and if you're talking of magnitude, let me say that these are all unit vectors but not necessarily orthogonal. Then won't these coefficients a convey the same thing? How much of x is along v1? That is a1. How much of x is along v2? That's a2, right?
No, sir, but to represent an entire space, we will need its basis, and for that we will need the linearly independent vectors.
Right. So my question is, yes, linearly independent is required for unique representation. Why orthogonality? Does it help at all?
So orthogonality helps in understanding vectors better.
What do you mean by better?
Means linear transformation and that operations become easier.
Give me an example. And as of now, all linear transformations we have discussed, we have, for example, the matrix representation or change of basis. We never talked of orthogonality, right? Anybody else wants to give this a try?
Because the projections of each other on each other are 0.
That is defining orthogonality. But why is that important? All you are saying is V1 inner product V2, V2 inner product V3, and V1 inner product V3 is 0. Right? But that's basically the definition of orthogonality. My question is that important to have representations of vector in terms of orthogonal vectors?
Like here we have coefficients a1, a2, a3. If we take linear independent, then we can represent a1, a2, a3 in more than one ways.
No, what do you mean by more than one way?
Like your representation of a1, a2, a3 may not
A1,
be.
A2, A3 are scalars. So we are not representing A1, A2, A3. We are representing X, right?
Then to find a1, a2, a3 with simple calculations may be difficult. But as we have seen in an earlier slide that x is a dot y plus w, then they are orthogonal vectors. So coefficients, to find coefficient is simple in that way.
Good. Yes. So if I want to represent a vector X in terms of its bases, let's call the bases as V1, V2, V3, right? I need to find these coefficients, right? How do I find these coefficients? As far as an inner product space is concerned. So what we can do is I can take inner product of X with V1. That's going to give me A1. V1 inner product V1 plus A2. V2 inner product V1 plus A3. V3 inner product V1. Similarly, I'm going to get system of linear equations. V3 is A1, V1 inner product V3 plus A2, V2 inner product V3 plus A3, V3 inner product V3. As a matrix, this is nothing but V1 inner product V1, V2 inner product V1, V3 inner product V1, V2 inner product V1, V2, sorry, this is V1 inner product V2, V2 inner product V2, V2 inner product, sorry, V3 inner product V2. This is V1, V3, V2, V3, V3 with V3. This times your unknown coefficients A1, A2, A3 is going to be equal to your right hand side vector that we usually denote by B. This matrix is, so this is, I hope you can see, this is like solving Ax equal to B, right? This particular matrix is called the Gram matrix. Okay? You probably will encounter this in your future course, some course at least. Okay? Gram matrix is nothing but the matrix formed by taking inner product of a set of vectors with itself. If V1, V2, V3 are not orthogonal, what can you say about the Gram matrix? Or to simplify the question, if V1, V2, V3 are orthogonal, let's denote this Gram matrix by G, then what would G become?
Diagonal matrix.
Diagonal.
It would be diagonal. And the diagonal matrix is surely easy to invert, right? If V1, V2, V3 are orthonormal. What can we say about G?
Identity matrix.
Identity matrix.
Yes.
Okay, so that is sort of the most important reason, and possibly in abstract math terms, this is the only reason why we would prefer orthogonal or orthonormal vectors. Okay, to find the coefficients, it's very easy. If you don't have orthogonal vectors, then you can see that the Gram matrix will not be a diagonal matrix, and so you will have to spend computations in order to find these coefficients. Okay, so I hope the importance is clear, and then we can sort of discuss this process. So if I give you a set of m linearly independent vectors which are not necessarily orthonormal, how do I convert this into a set of orthonormal vectors E1 to Em with this particular condition? Okay, and this, once you sort of understand this condition, what this says is, if I want to obtain the first vector in this orthonormal set, I should only use the first vector of this linearly independent set, right? If I want to find E1 and E2, right, the first two vectors from this set of orthonormal vectors, I should only use the first two vectors V1 and V2 in order to obtain this, right? So on and so forth. Is that clear?
Yes, sir.
So I'm going to follow the same process. E1 is just, since all we need is E1 must be a unit norm vector, so I can just define E1 as V1 divided by its norm, so that the norm of E1 becomes 1. Okay, so let's say this is my E1, this is my V2. First vector E1 is just a unit vector along V1. Okay, what would be my second vector E2 be? So we have already seen, I want E2 to be such that E1 and E2 span V1 and V2. Therefore, it implies that E2 must be obtained via a linear combination of V1 and V2. So what I can do is I can use the orthogonal decomposition of V2 along E1. Okay, so what I plan to do is V2 can be written as some A times E1 plus some vector, let's call it W, such that W is orthogonal to E1. And then use that W in order to get E2. Okay, so that's exactly what this expression here over says. Okay, so draw the picture here. Right, so this would be my vector Y, right? Or the vector W, sorry. This would be my W. And this would be V2 minus V2 inner product E1 divided by E1 inner product E1 or E1 norm squared, but norm of E1 is 1. So get W equal to V2 minus V2 inner product E1. Instead of calling it W, let me call it E2 tilde. Okay, so from this vector W, what should be my E2 be?
Double divided by norm.
Exactly. all I want to do is I want to ensure that E2 is a unit vector. It is already orthogonal to E1. So this is E2, which I hope you can see is exactly this. Okay. Similarly, E3 will be V3 minus, so in terms of R3, I were to draw a picture. So think of this as V1. Make my job easier. Think of this as E1 and E2. This is my V3. 3 will be just this. This is my E3. Remember, even though I'm drawing it here, I draw it here, assume that it is this vector that I'm talking about. Okay, so this will be my vector E3 tilde. Okay, so in order to obtain E3, it will be just E3 tilde divided by norm of E3, which is just this equation over here. And in general, the idea is Ek would be Vk minus inner product of Vk with Ei into Ei, summed over I going from 1 to k minus 1 divided by its norm. I hope, I'm not sure if the fonts over here are visible or not. If not, I can zoom in a little bit. Okay, but I hope you got the idea of what we are trying to do over here. Okay, and now by construction, right, observe that this condition is satisfied. Okay, in general, we'll have to prove that this set E1 to EM is orthogonal or orthonormal. Okay, so we are going to prove this by induction. The base case is easy to see that E1 and E2 are going to be orthogonal. Okay, why? E1 times this E2 minus V2 E1 divided by this. So maybe I make my job a little easy by calling the numerator of this as E2 tilde divided by norm E2 tilde. What would this be equal to? Is norm V1 into 1 by norm E2 tilde V1 E2 tilde. What would be V1 E2 tilde? This is V1 V2 plus V2 even, sorry, minus, not plus, minus V1 even. Right? So what would this be? Can you show that this is 0? Right? This is nothing but your vector y, right? Or your vector, sorry, w. Okay, so try to show that this is 0. And this is clear. Can I assume it is clear? Are we going too fast or is it okay? So in general, right, the induction process says that let's assume E1 to EJ are orthonormal, and we are supposed to show that if I include EJ plus 1 in this, I still have an orthonormal set. Okay, so EJ plus 1 is nothing but E tilde J plus 1 divided by EJ plus 1 norm, EJ plus 1 tilde norm. Okay, so in order to show that this larger set with J plus 1 vectors is also orthonormal, since E1 to EJ are known to be orthonormal, all I have to do is to show that the inner product of EJ plus 1 with any of the previous vector, right, EL, where L goes from 1 to J, I have to show that this inner product is 0. Okay, so as we did in the previous case, EJ plus 1, I have defined it as EJ plus 1 tilde by norm. So this norm can be brought out, and EJ plus 1 is nothing but VJ plus 1 minus this summation. Okay, so if I take the dot product of this with EL, using linearity, I get VJ plus 1 dot product EL, or inner product EL, minus linearity again. So I can bring out this constant here, Vj plus 1 inner product E1 into EI inner product EL. Okay, now what do we know about EI and EL? EI and EL, for I going from 1 to J, you know that E1 to EJ are orthonormal. So this dot product has to be 0 unless I is equal to L. Okay, so for I equals L, this summation becomes Vj plus 1 inner product EL. But that's exactly what is over here. Therefore, you get 0. Okay, so that is how you sort of prove that whatever process or algorithm you have stated, it's going to give you both required conditions, right? The spans are going to be maintained as well as orthonormality is going to be maintained. Let's move on to what is called the orthogonal complement of a set. Okay, so if V is a finite dimensional inner product set, right, and let us pick any arbitrary subset U of this inner product space V. Once again, it's U is supposed to be a subset, not necessarily subspace.
Sorry to
Yes,
interrupt, sir. Can you explain the zero part again in the previous slide?
this one.
Yes, sir.
Okay, is this expression clear?
Mm. So, means.
Okay, let me redo this then. Okay, I want to find the inner product of EJ plus 1 with EL, right? Where L goes from 1 to J. Now, what is EJ plus 1? It is EJ plus 1 tilde by norm EJ plus 1 tilde with EL. Okay?
Yes.
I can bring the constant out. I get EJ plus 1 tilde with EL. Okay?
Yes, sir.
Then this is EJ plus 1 tilde norm. What is EJ plus 1 tilde? You can see over here. EJ plus 1 minus summation I equals 1 to J. Vj plus 1 EI
EI.
and EI.
EI.
EL. Okay?
Yes, sir.
Is 1 by norm EJ plus 1 tilde. I'm using linearity of my inner product to get this with EL minus some, these are just constants. So I equal to 1 to J
Yeah.
Vj plus 1 EI EI EL. that okay?
Yes, sir.
Okay. Now, what do we know about EI inner product with EL?
They are also normal. No.
So EI and EL are ortho normal vectors.
Yes, sir.
So the dot product or the inner product is 0 unless I is
I
equal
not.
to L.
Yes.
So that gives me this Vj plus 1 EL, right? So if I is equal to L, then this becomes
Will be
1,
1. Yes.
otherwise 0.
Hmm.
Rather than having these j terms, I will have only one term. It would be Ej plus 1 EL.
Yes, both are same 0.
Exactly.
Got it, sir. Thank you.
Right. So we were looking at any arbitrary subset U of an inner product space V. For this U, we define its orthogonal complement as the set of vectors in my vector space V which are orthogonal to each and every vector U of my subset capital U. Okay. Maybe if you want, we can do an example here. So let's consider R2. This is my theta. What is the orthogonal complement of theta? So what vectors in R2 are orthogonal to this theta or the origin?
Sir, all the vectors.
All vectors. So theta's orthogonal complement is R2. How about U being given to be this vector 1, 0? What is the orthogonal complement of U? Write it in the same color so that then we'll track this in the slide. If this is my U, right, this single vector, what all vectors are orthogonal to this single vector? And where I'm assuming the usual Euclidean inner product. Okay, please be careful. The definition of orthogonal complement depends crucially on the definition of inner product. Okay, so unless the inner product is defined, you cannot find out the orthogonal complement. Okay, but for now, assume that whenever I do not define specifically the inner product, it is your usual inner product, okay, that you are familiar with. So what is the orthogonal complement of the vector
So
1,
then
0?
it is 0, comma b, where b belongs to R.
Exactly. So the entire y-axis. If this is your unit vector along x, then any vector on this line is, so rightly said, this. How about, let's say I take this set. This line, this entire line. And that passes through, I don't know, let's say 0, 1. So this entire line, if this is my set U, then what is the orthogonal complement? Anyone? See, how many linearly independent vectors are there in U? So this vector is in U, this vector is in U. Are these two vectors linearly independent or dependent?
Sir, independent.
Now, if a vector is orthogonal to two vectors, will it also be orthogonal to its linear combinations? Question is, if B inner product U is 0 and B inner product W is 0, what can you say about B inner product sum AU plus BW?
Zero, sir.
Zero.
Also,
Right? So even though your U contains all vectors on this line, right? Basically, if you know sort of you take two, basically take these two vectors, right? Using these two vectors, you can construct the entire U, isn't it? So instead of trying to find vectors which are orthogonal to all vectors on this line U, you can also try to find vectors which are orthogonal to two of its vectors, or basically vectors using which you can obtain all other vectors on U. If I call this as U1 and this as U2, right? If V is orthogonal to U1 and V is orthogonal to U2, right? Then equal to 0, 0. Then V is orthogonal to U, where U can be any vector in U, right? Because the line or the set U is nothing but obtained by linear combinations of U1 and U2. So what vectors are orthogonal to both U1 and U2? That's where the question boils down to.
none in R square.
Once again,
No vector in R square will be
no
orthogonal
vector
to
in
them.
R square. Are you sure? What about theta?
Yes, theta will be.
Right? Theta will be orthogonal to both U1, U2, in fact, to anything. So, can there be any non-zero vector which is orthogonal to this set U? There cannot be, right? Because this is R2, U contains two linearly independent vectors. So this is a basis of R2. If there is some vector which is orthogonal to both U1 and U2, we just saw that it has to be orthogonal to any linear combination of these two vectors, right? But any linear combination of U1 and U2 is going to give you any vector in R2. So if there is a vector which is orthogonal to U1 and U2, it has to be orthogonal to the entire R2. So the only vector which is orthogonal to all of R2 is 0 or theta. Okay? That comes from this property that if a vector is orthogonal to n vectors, then that vector is also orthogonal to any linear combination of those n vectors. Right? I hope I'm making sense. And then as these three examples show, is there any doubt here? If you want, we can look at more examples. You can come up with your own set U and let us try to find out its orthogonal complement if you want. Otherwise, we can proceed. The idea is clear. Okay, then I'm assuming you are okay with this. So I'm going to leave this question as a homework, as you can see on the slide, and as shown in these three examples, you can see that in the first two, in the second example, U was not a subspace. It just contained the vector 1, 0. So U is not a subspace, but the orthogonal complement of U, irrespective of whether U is a subspace or not, was always a subspace in these three examples at least, and this is not a coincidence. You can show that this is always true. Any doubts here? Okay, then let's proceed with one of the most important concepts as far as inner product spaces are concerned. Okay, so now let U be a subspace of a finite dimensional inner product space V. Okay, then I can surely write V as a direct sum of U and the orthogonal complement of U. Do you agree with this? Is that clear why this should be true? So if U is a subspace, right, U perp is also a subspace, right? Will U plus U perp be equal to V? Right, that's the first question. And the second question, which is easy to see, is the intersection of these two has to be only 0, right? That I guess, I mean, all of you who are okay with this, right? Because U intersection U perp will contain all vectors in U which are orthogonal to themselves also. So, of course, that means that you can only have theta here. What about this? Okay, maybe think about this. If you are not able to show this, then we can prove this in the next class. But I think you should be able to do this. Okay, so for now, assume V is the direct sum of U and U perp. Now, let us define a linear operator on V, okay, such that, and how do we define this? So, any vector V in my vector space V can be written as a sum of two unique vectors U and W, where U comes from U, W comes from U perp, or the orthogonal complement of U. Now I'm going to define PU subscript U applied to V as giving the component of V in the subspace U. That is the definition of my linear operator. Clear? Then are we going too fast? I can sort of I sort of feel I'm losing some of you. At least some of you, maybe all of you, I don't know.
Sir, I'm also hanging out. Sir, we are choosing you such that the direct sum of u and u, the orthogonal complement of u is gives v, or u is any subspace of v.
U is any non-zero dimensional subspace of V. Okay, let me put it that way.
Okay, means this will be true for any non-zero dimensional subspace.
Yes.
Okay, sir.
Okay. In fact, I mean, this non-zero dimensional assumption is only going to play a small role, but V written as U orthogonal sum, sorry, direct sum U perp is true for any U. Because if U is theta, right, U perp will be V.
Yes, sir.
Okay. So, but yes, I did not choose any particular subspace. Okay. U could be any subspace of this finite dimensional subspace, sorry, finite dimensional inner product space V.
Yes, sir. Then this linear operator simply chooses the component of v along the direction of u.
Not direction of U, in the subspace U. U is not necessarily one dimensional.
Yes, sir. In the subspace u. Yes, sir.
Yes. This PU defined above is called nothing but the orthogonal projection operator on the subspace U. Okay, the orthogonality comes because the other subspace is U perp. Yeah, I guess, I mean, the name is something you are familiar with, possibly. You may have used this in geometry. Right. Let's look at the property. And I think this is very similar to one of the questions we did in the last week's tutorial. So what is the range of PU going to be?
Sorry, u.
U. Good. What about the null space or the kernel of PU?
Sir, u perp.
U perp.
U perp.
What happens if we apply PU twice? PU applied to PU applied to V. PU applied to PU applied to V is equal to PU applied to PU applied to V. What is PU applied to V? PU applied to V is U. So PU applied to small u. What is PU applied to small u?
U.
U, which is nothing but PU applied to V. Okay, so again, it doesn't matter how many times we apply PU. Once we apply it once. Okay, this property for any linear operator is what is called idempotence or idempotent. Moreover, okay, if let's say the vector, sorry, so this is not U, this is a typo from my end. If the vector space is Rn or Cn, right, for now let's think about Rn. What can you say about PU transpose? So let P1 PU1 plus W1 and P2 PU2 plus W2. Okay, where UIs come from U and WIs come from U perp. what is the dot product of PU V1 with, let's say, U2 or Euclidean dot product? So remember, our vector space is Rn, so this linear operator is nothing but a matrix, right? So basically I can write this as this matrix PU operated on V1 dot product V2. What would this be equal to? What is PU operated on V1?
U1.
U1 with V2. So this is nothing but V2 transpose U1. Okay? And U1, as we just said, is nothing but P applied to V1. Similarly, what happens if I use this V1 dot product with PU into V2? What would this be equal to? What is PU multiplied by V2 going to be?
U2.
U2. This is by definition U2 transpose V1. What is U2? That's PU into V2 transpose V1, which is V2 transpose PU transpose V1. Okay? Now what? So please keep these two in mind. Okay? What is V2 transpose U1 going to be equal to? What is V2? What is V2? V2 is U2 plus W2. What is U1 inner product W2?
0.
0. This is just U2 transpose U1. Okay, keep this in mind. Similarly, what is U2 transpose V1? Is V1 inner product U2? What is V1? It's U1 plus W1. It's U2. Is U1 inner product U2 plus W1 inner product U2. What is W1 inner product U2?
0.
0. This is also U2 transpose U1. So from 3 and 4, what can we say? And basically from 1, 2, 3, 4, what can we say? So 1 and 2 are the same, isn't it? Because this is 3. This is 4. And 3 and 4, we have just shown that they are same. Okay? So therefore, V2 transpose PU V1 is the same as V2 transpose PU transpose V1. And did we assume anything special about V2 and V1? No. They could be any vector in Rn. So when can this be true? When can this be true? Have I lost all of you? I know I have overshot the time.
When PU is equal to PU transpose.
Transpose. Thank you. Okay, so orthogonal projection operators on Rn, right, when represented as a matrix, the matrices will be symmetric. Okay, that's a important property to know. And instead of Rn, if we had assumed that the original vector space was Cn, in that case, instead of transpose, you would get complex conjugate transpose. Okay, so such matrices whose complex conjugate transpose are equal to the same matrices, these are called Hermitian matrices. There's just one last property that I wanted to derive and talk about as far as orthogonal projection is concerned. Can I do that and then finish this lecture?
Sir, can you give the definition of Hermitian matrix again?
Sorry?
Can you repeat the definition of Hermitian matrix?
Hermitian matrix, a square matrix with complex valued entries is said to be Hermitian if its complex conjugate transpose is equal to itself.
Okay, sir.
Okay. So I'll just repeat the same question. There is one more important property that is going to be utilized in several applications that I wanted to discuss as far as orthogonal projections are concerned. Can I just take 3-4 minutes more and then stop, or are you tired and you want me to take this up in the next class? Can I discuss one more property or no? I mean, you've had enough.
Yes, sir.
That was a very damp yes. But anyways, let us see. If we'll discuss this, if you're still not clear, we'll start with this property again in the next class. This is something which is very intuitive. It says is for any vector v, the orthogonal projection of v to the subspace U is the vector that minimizes the distance between the original vector v from any vector in the subspace, given subspace U. Okay, so what I mean by that is if this is my subspace U, this is my theta, if I take a vector v over here, okay, then the point in this subspace U which is closest to this point v is the same as the one obtained by orthogonal projection of v to the subspace U. So this. Why should this be true? Okay, I won't harass you guys more. I'll just quickly go to the derivation here. So let U be any arbitrary vector in the subspace U. Okay. I want to find the distance between V and U, so distance squared. Okay, which is this. Now I can add and subtract a vector in this without affecting the distance. Right, so that vector that I'm subtracting and adding is PUV. Okay, do you agree with this? These two cancel out, you get the same thing. Now what can we say about this vector and this vector? So what can you say about PUV minus U?
So it belongs to the subspace U.
This belongs to the subspace U. And how about this vector?
This is orthogonal to U.
So therefore, this belongs to U per.
Yes.
Okay, so these two are orthogonal. So what from the Pythagoras theorem, you can say that this is equal to V minus PUV norm squared plus PUV minus U norm squared. What can we say about this norm squared? It has to be surely greater than equal to 0. So therefore, for any vector U in U, right, the distance of this vector U from the given vector V has to be greater than equal to the distance of V from the orthogonal projection of V to the subspace U. That is exactly what we wanted to prove. Okay, so it's not a coincidence that, so first of all, orthogonal projection, we have not used distance at all to define that. Okay, but because of the orthogonality, it is a property that the distance is minimized by that orthogonal projection. And once again, remember, this norm is the same, is the induced norm of the inner product. So if I change the inner product definition, this norm's definition also changes. Okay, so with that, I'll stop for today. Apologies for taking up 10 extra minutes. This will ensure that in the next class, we won't sort of have to hurry up something. Okay, there's just two things that I wanted to discuss in the next class. Hopefully, it won't take an entire hour and 15 minutes. It should be done hopefully in 45 minutes. Since that is also the last class of this course, I would appreciate if you could let me know verbally, right, how the course went, where did I go wrong, and where did I go right also. Okay, but I'm more interested in your critical feedback, right? So don't think that I will penalize you, so therefore you should say only good things. I want you to sort of come out with your critical feedback on the course, all aspects of it, exams, tutorials, lectures, etc. etc. So thank you. See you guys. I hope to see as many as possible in the next class. Thank you.